Today we'll be talking about parallel wiring. Parallel wiring means that the devices are connected in such a way that the same voltage is applied across each device. So what does that mean? Well, we have two resistors here. They're both attached to the left-hand side of the battery and to the right-hand side of the battery. This is a more traditional way of showing that same circuit. They're both attached to the left-hand side and they're both attached to the right-hand side. When two resistors are connected in parallel, each receive current from the battery as if the other wasn't present. So what does that mean? Let's imagine this is a light bulb and it goes out. Will this one keep on working? Yes, it will, because it still has a current path for the current to go through. Therefore, two resistors connected in parallel draw more current than does either resistor alone. So let's think about this. Is your house wired in series or in parallel? Well, if it's in series, there would only be one current path and the voltage would divide across the devices. In parallel, each device would maintain the same voltage drop, but there would be different paths for the current to flow. So which one would make more sense? Hopefully you thought that it was parallel. Because imagine you had a circuit that you had to turn on the TV just to get the toaster to work. That would be kind of ridiculous. That would happen in a series circuit because there would be only one current path. Alright, imagine that you have two pipes. As you add pipes together, you have more branches for the water to go through, or more pipes for the water to go through. So as you add more branches, there's more cross-sectional area, and the resistance to flow will go down. So more branches, less resistance, more water would flow through. So the same thing is true with electric circuits. More branches, less resistance, more current. So let's talk about how we add parallel resistors. We know that the total current that comes out of the battery has to equal the individual branch currents. We also know from Ohm's law that current is equal to V over R. So I can replace I with V over R. And I know the V is the same for both resistors, so I can factor out the V. So now I have a way of adding resistors in parallel. Resistors in parallel are added using the following equation. So let's try an example. Here we have a receiver that is connected to remote speakers in addition to the main speakers. What we'd like to do is know the equivalent resistance of the two speakers, the total current supplied by the receiver, the current in each speaker, and the power dissipated by each speaker. This is actually an AC circuit, but we can ignore that fact and assume it's DC. So the first thing we're going to do is find out the equivalent resistance. Use the equation we just determined. We find out the equivalent resistance is 2.67 ohms, which is much less than either one of the original resistors, because as you add resistors in parallel, the resistance goes down. And using Ohm's law, we could find the total current that goes through the equivalent circuit. So the total current that goes through the equivalent circuit is 2.25 amps. Now I'd like to find out what the current is through each of the branches. And using Ohm's law, I could find the current is equal to V over R. The V is the same for both of them. And I can find the current. And to find the power, all I have to do is use the power equation. More current times the individual voltages. So it's pretty straightforward. So sometimes we have circuits that are wired partially in series and partially in parallel, like this one here. So how do we simplify this? It's really not that difficult. First, you add any resistors that are in series or in parallel with each other, and you keep on reducing the circuit down further and further until you get simpler and simpler. So right now we know that this 220 ohm and this 250 ohm resistor are in series, so we add those two in series. So we end up with 470 ohms, and now the circuit reduces down to this. Okay. Then we take these two resistors that are in parallel, add them together. The 180 and the 470 are in parallel. Add those together, and we have an equivalent resistance of 130. Now the 130 and the 110 are in series. So we add those together in series. And we end up with the equivalent resistance of that big circuit is this little guy here. It ends up being an equivalent circuit of 240 ohms. So using these techniques helps you reduce a very complicated circuit down to something simple. And these techniques work pretty well unless you have two batteries. And if you have two batteries or two voltage sources, you end up having to a lot of times use Kirchhoff's laws to reduce those, as we'll see in the next video.